So we've been discussing how to raise an index. So let's rewrite this last boxed equation as a matrix equation. So the position vector, the contravariant position vector, has got components t, x, y, z. So that's x mu upstairs. And then we've got the Minkowski metric. There's 1, 0, 0, minus 1, 0, 0, minus 1, 0, 0, more zeros. So there's the Minkowski metric. And then we have the covariant vector, which is t minus x minus y minus z. So this is just a rewriting of the boxed equation as a matrix equation. And I just want to mess around with it a little bit just to understand the translation between the boxed equation and a matrix equation. So if I was to look at a specific component, let's say that I look at x from the left-hand side. So x would be equal to, it'll be 0 multiplied by t plus minus 1 multiplied by minus x plus, next we've got 0 multiplied by minus y, and finally 0 multiplied by minus z. Okay, and that nicely lands up giving us 0 times t is 0, minus 1 times minus x is x, 0 times minus y is 0, 0 times minus z is 0, 0 plus x plus 0 plus 0 is just x, so that indeed this equation is correct. But let's just interpret each of the terms that are being summed. So this 0 over here is eta 1 naught, and the t is x naught, plus the minus 1, well, that's eta 1 1, and the minus x is x 1 downstairs, the covariant x1. The naught here is eta 1 2, so row 1 column 2, that's the naught, times by the minus y is the second component of covariant x, and finally we've got the naught, which is eta row 1 column 3, and then minus z is the covariant, the third covariant component of x. So what you can see is this matrix multiplication is indeed just the Einstein summation convention. So I hope it's completely clear how this boxed equation can be rewritten as this matrix equation. Good. And we have some language to go along with this. We say that we used the metric to raise the index of x nu. So by acting with the metric, we have raised an index. Okay, so covariant position vector x nu was raised into contravariant position vector x mu. We can also lower an index, so we'll have x mu. Now we need something with two lower indices and contracted with contravariant vector x nu. So here we would say we have lowered an index, and I would need to tell you what the components of eta mu nu are. Well, it turns out that the components of eta mu nu are exactly the same as the components of eta mu nu with two contravariant indices. So whether the two indices are contravariant or covariant doesn't matter. The matrix elements are the same. And now you know all of the ingredients inside this equation. You know covariant x, you know contravariant x. So you could actually check, is this equation that I have written down here, is that equation true or not? So you should check that equation and see if it works out. Now, How does covariant vector transform? Well, there is covariant vector. So let's write x primed mu is equal to lambda mu x nu. And remember, lambda was this matrix representing the boost that we've studied, okay? So this is how a contravariant index will transform. We're also going to need the rule for how will a covariant index transform. And let me call this matrix alpha tilde. There will be an alpha and a beta and an x beta, okay? And of course, lambda specifies the Lorentz transformation. So I would expect that I can write lambda tilde in terms of lambda. And that's what I'm going to try to do now, okay? So let's start off. So x primed alpha, well, I can use the Minkowski metric to lower the index of x prime. But when I've got it written in this form, well, I can use the first equation in the box to write this as eta alpha beta lambda beta, let's say, nu x nu. And now I can use the metric again to lower the new index. So I can write this as eta alpha beta lambda beta nu eta, let's say, nu mu x mu. And we also know, by looking at the boxed equation above, that this will be lambda tilde alpha mu onto x mu. So we now obtain a formula for lambda tilde by comparing the last two lines of what we've written down. So what do we learn? Well, we learn that lambda tilde alpha mu is equal to eta alpha beta lambda beta nu eta nu mu. And I think this is a lovely intuitive formula, because you can see that to get lambda tilde from lambda, we lower the first index of lambda and raise the second index of lambda. Okay, now that we know how both covariant and contravariant indices transform, we can work out the transformation rule for any tensor. So for example, let's consider T primed mu nu alpha, okay? So what is this? This is a rank 3 tensor. It has got 2 contravariant indices and 1 covariant index. For each contravariant index, I will have lambda transforming the index. So I've transformed the 2 contravariant indices, and then I still have the covariant index. And let's make this alpha and tau, and that is tau. So this is how this rank 3 tensor would transform. And what does this equation mean? Well, if I have this rank 3 tensor in one Lorentz frame, T gamma delta tau, and I want to work out the components of this tensor in the primed Lorentz frame, this equation that I've written on the bottom of the page tells me how to work out the components of the tensor in the primed reference frame. So I know how to work out how the components of the tensor change under any Lorentz transformation. So that means under any rotation or any boost or any combination of rotations and boosts, any sequence of rotations and boosts. And we know things extremely explicitly. So lambda, well, here is lambda. The first thing that we wrote down was lambda. So we know this matrix corresponding to a boost along the x-axis is the matrix elements of lambda. You could write a boost along any direction, or you could have written a rotation. And then we also know what eta, the Minkowski metric, is. So when we look at lambda tilde, well, we know eta, we know lambda, we know eta, so we can very easily work out what lambda tilde is. So we know both lambda and lambda tilde, which means we know exactly how any tensor will transform when we move from one reference frame to another reference frame related to the original one by any Lorentz transformation.